Great. So last time we were starting to be able to discuss more of the topics related to dealing with, all right, well, what if I, in some ways, want to make these models more scalable? And we were talking about deep reinforcement learning in this particular case because it is unreasonably or surprisingly difficult in order to get them to train on data. They tend to need to see things thousands of times before they actually start to learn, okay, this was a good thing to do. This is a far cry from what people are able to do most of the time when learning. And we were starting and talking about this concept of handling, it's called experience replay, which is just you've got some data sets, and at least in RL, this data set is not fixed because the agent keeps collecting new stuff, getting rid of old stuff because it's got some limited memory. But this thing basically changes over time. But you would like to be able to not throw out data from this before the agent has really learned a lot from that data. Ideally, everything it can, but that's not typically what happens. So this is a little bit about, in this case, we want to, for the algorithms that we can be making, we want to be able to basically increase this K for as much as we possibly want, and things still don't diverge. And then also a little bit in the space of, it'd be good to be able to increase capacity, because now when we can make K bigger, we can probably develop algorithms such that we can train better agents, but then we can give them larger problems to actually work on, probably making the capacity of our models larger as well. Okay, so let's talk a little bit about why that's difficult. So we would want to be able to scale some of these models and algorithms for RL, but it becomes a little bit trickier to be able to do this for larger and larger models. And this is really because kind of for two reasons. I mean, RL, as I said, it's generating this non-IID data from here, which basically deep learning, machine learning, it says sort of like, cool, things will work if my data set stays the same, everything is IID, I should be able to converge to something. And then RL, for the most part, breaks all of these assumptions, even though it's been working for the last 10-ish years when trained very carefully. So this tends to grow. So maybe one question we can start to think of and discuss some ideas here. Why do we start to think this problem even grows to be worse for larger and larger network models? So it has been a struggle in the community that if you're going to train a DeepRL policy, I only know of about 3 or 4 papers that could train from scratch a DeepRL policy that used a transformer. And there's they managed probably to get their hyperparameters perfect or something in that case, but it's been a real struggle. So any ideas about why is this more problematic when we have a larger model? So at least in an average DeepRL paper, normally what is used is a 2-layer deep network model that's just 2 layers of 256 units, or a simple convolutional neural network with 3 convolutional layers and maybe 1 feed-forward layer. How come we can't get either more layers added onto this model very well, or why we just, for the most part, seemingly can't use transformers from the beginning either? So I guess at the moment, more complexity, I'll go with the deeper models. Although complexity is a great term we can dig into more and think about the function space of possible things that could be learned by the network. Yeah, does that help? Okay, so maybe I'll say how come I can't train, or sorry, why does it seemingly seem to be more difficult to be able to train a deep RL policy if I had a 20-layer network instead of a 2-layer network?
It's hard for the network to converge on something like that. It takes a lot of training. Maybe you're limited hardware. Most of papers are hard to replicate sometimes if you don't have the weights, because it's nearly impossible for you to train the network. You don't have that much data or power.
True. I think we need to dig into harder, what we mean by harder a bit more. And then because there's more and more layers in the network too, you can get uglier and uglier gradients. That's certainly part of it. But I mean, there are lots of other supervised learning setups that people are using, well, that we can train deep learning models. They've figured out ways to deal with those gradients, so that you could still train a model that would converge. So then what is it about like the RL case that says, well, no, those methods, those tricks still don't work well?
That's what you're learning. You're learning the function, right? Then you're trying to it's based on the convergence of the Q function. So and then it uses the previous output that the Q function gave. So kind of an exploration. So when we have a larger network, it's harder for the Q function to converge with the optimal policy.
Mm-hmm. Okay. Yeah, I'm going to go into a bit more detail about all of these. One of the ways, there's a high-level way to discuss this, which I'll draw a picture here on the left, which kind of encapsulates some of these, where if you've got, so this thing kind of, this difficulty in order to deal with this happens a lot in what's called like stochastic, well, it's called stochastic policy ascent, which is a little bit different than stochastic gradient descent. But it means that you want to do a update on your actual model with whatever batch of data you have right now. And it might make some change in policy. It's the distribution of outputs that actually come out of the network. And then the problem is we don't entirely have control over like how much can that distribution change when you do like a single update on your actual like deep learning network. And part of the hypothesis here is the part that makes it harder and other challenges. And now if you have a deeper network, which means somehow you're getting larger gradients, might also implicitly say, okay, the distribution of possible outputs when you make a single update can be much larger because you've got basically a much larger composition of many functions across many layers. Who knows how much this can change? This means it can destabilize training much easier or earlier in the training process. Because normally you'd want this nice process. You can think of our agent or its policy trying to find like the high point on this hill. And you'd want to make smaller steps such that each step still stays on this hill and you're making at least incremental improvements. But it's possible that when we have larger networks, like doing one update results in this much larger change in the distribution. It's not so bad in supervised learning. We can make really, really small learning rates and a number of other tricks. But part of the challenge in DeepRL is, okay, if you make a small learning rate, it's challenging because actually you want your agent to pick up on the new information it's learning from. If you make a really small learning rate, it might not even learn from the stuff it generates because it's going to get swept out of the buffer. And you'll never have your agent actually pick up on it. So there's a more of a delicate balance of trying to get these algorithms to work, to pick up on things, to be able to balance data collection, data learning, and basically the amount of change that will happen in the policy for any single update. We'll talk about more this in a bit, but this is why like stochastic policy gradient methods like PPO and TRPO, they usually have some constraints. You can make an update, you can change no more than this much. Because anything beyond that, we know it's mostly, we always end up getting in a bad state where the network is basically diverged and no longer useful. Does that make more sense? Great. We'll basically have like 2 whole lectures on how to deal with this and kind of the details of each of those little problems that might go on. So this is where, we'll talk about maybe some of this can be helped if we do like resets on the network, which basically is kind of like saying, all right, the agent has made some progress and maybe it's gotten a little bit off track from this part here. If we reset some of the network, basically such that it's a new random initialization, we're kind of throwing it back onto this path. Even if it's maybe lost some information, it still won't diverge. You can add some constraints on this, basically other forms of constraints so the distribution can't change too much, because some of my recent work. This part, the community is excited about, but I still think it's a little more difficult to reason about. But maybe there's something about the way we can train large models in the future that can refine us down to this nicer distribution of potential changes to that policy such that you can't deviate too much. So like even though you have a huge network and the way like language models are trained these days for RLHF is you do optimize the RL function and the reward a bit, but then you're constrained by some KL constraint. Don't get too far away from the original LLM model. So there might be some other constraints that just says like, here's a good prior, start here, don't get too far. And that might help prevent some of these larger problems with like distribution changes and divergence. That is definitely still an area of work. Yes. Yes. In fact, it does. Okay, implicitly, it might be a little bit easier when you have a finite number of actions. I'm mostly only saying that because a lot of this work, which hasn't been a lot of it so far, that goes into scaling DeepRL algorithms, is mostly studying discrete action problems with small actions. It hasn't been working well or at least hasn't been studied as much for other problems with larger numbers of discrete actions, or continuous actions has been tricky too. But it depends. I don't think that's entirely like a strong claim what I just made. Because I would say like doing RLHF on a transformer means that the number of actions is like the tokenizer. So there's probably like 40,000 actions it can possibly take. So that's pretty big to me. And it still can work well. But most of the, where we'll start on talking about this is scaling DeepRL from scratch, which is a lot of an optimization problem. Maybe some of the learned priors will help, but that's still for the community to figure out. Great. And that's what I was saying here. Like most of this work's been done on DQN. So far, there's like one or two things that have worked for PPO because PPO can be even more wild. And by wild, I mean it can be more stochastic because it's a stochastic policy gradient method. So you can't control the changes as much. Okay. So still, if we think about it a little too deeply, sometimes it's surprising that deep reinforcement learning works at all, because sure, we might be trying to fit a value function in this case, which is just something that says at this state, if you happen to know like the agent's normal policy, it'll get this performance into the future. But this ends up technically the way you train a lot of these particular models is being able to use Bellman error, but this is not the exact same as getting the reward. So you're kind of training this other objective that technically, if you know a lot about learning contractions, which we'll talk about later, means that eventually you start getting a better model for actually how to predict the reward, but you're not actually optimizing for the thing you care about, which is increasing the reward for the agent. So it's kind of weird that it still works. Like I said, it can mean that these algorithms can diverge really easily because now you're kind of like bootstrapping some prediction of what you hope to be the reward for the agent, but we're not exactly sure. Yeah, there's always this odd one for model-based RL. It also has this problem. So if your hope is to train a world model, there's nothing that really says if you improve on the accuracy of your world model, the agent will actually improve on the sum of rewards it gets. Those are two different things. You can't really connect them unless you perform a whole bunch of other stuff that's kind of entirely outside of the normal design. So it is occasionally odd that things like Dreamer work well because they don't, if you improve on your model accuracy, doesn't actually theoretically result in improve on rewards. It's not until your model magically becomes completely perfect that technically you can have some connection there. But we never have perfect models. And this class will never have a perfect model ever, and we will work with that assumption. Yeah, and the part that does do what it's intended, and it's pretty clear, is to do a policy gradient method. You basically sample a bunch of rollouts from your current policy, adjust the probability distribution to repeat stuff with higher likelihood for the things that get higher rewards. And just do this repeatedly, incrementally increasing the performance of your policy. That one, at least mathematically, sounds nice. It is also one of the more tricky ones to be stable because it's more stochastic, but it has this really nice lever where like it works better if you just collect more and more batch data, and it seems to get a smoother gradient and work. That's why one of the reasons it's nicer to work with. Okay, does that make sense so far? All right, great. So, and then along with this too, there's also a lot of assumptions, in particular in this class, that will basically break from like step one. So common assumption one, full observability. If you're doing robotics, you never have any kind of full observability. And to be honest, even in simulators, you never have full observability either. But this really depends on whether or not you want to talk about like basically loss and accuracy of different floating point operations in the computer or other issues that happen, but they just don't really matter that much in the simulator. Episodic learning is an interesting one. So like for the policy gradient case, to be able to optimize your policy, you need to be able to have an initial state distribution and reset your policy and technically visit every single state that's possible inside of that environment. This is a pretty strong assumption. You know, how many of you have visited every single state in your life repeatedly 1,000 times? And that's what's been important for you to be able to get a good policy. Okay, good. No one fell for that one either, because we have supposedly, you know, a linear version of time. So we can never, as far as I know, remember, go back to any point in time and revisit that and try a new action and see how it works. We tend to just ignore all that stuff that we can't actually do anything about. Probably helps us sleep better. Oh yeah, and then like there's a lot of continuity and smoothness assumptions in most of the proofs for RL that, you know, all the tabular stuff means you either have like a linear model or you've got a tabular model and then you can converge from there. But this is robot learning. We're going to be using all nonlinear function approximation, which means that all those guarantees are gone. But we still want all those benefits without having to be tied down to linear models. Okay. All right. So this one I definitely wanted to talk a bit more about. If the goal, at least for the topic of this class, is to make, you know, some embodied AGI system, does I'll call it the embodiment, the morphology, or the robot, is that actually important? So maybe you can close your eyes for a minute. I don't know if you know what an amoeba is, but picture yourself as an amoeba, which is like this small little, I guess it's a single cell organism. I'm not a biologist, but like, what could you learn? You can really only interact. I would guess that as an amoeba, we can only travel, what, like a meter in our entire lifetime. So you're only going to, at most, experience that much in your life. So what can you really learn? What can you actually affect in your world and force you to be able to learn stuff? So, and there's even some in the community that are saying like, really, there's no such thing as AGI if it doesn't have some form of embodiment. Like, does our intelligence from the people, whatever, in the entire world, is it tied really strongly to the way we end up interacting in the world and the stuff we can do? So that's where, like, if the agent that we're training is only a stationary arm, it can only learn about stuff it can reach. It can only do those things. If it's only a car, it can only travel on things that are paved outside. It can only go so fast. It can't actually pick up stuff in the world so far. I gave the amoeba example. Okay, a humanoid robot could be a good start. And there's definitely a lot of incentive out there, it seems, to be able to make humanoid robots. But I also like to pick this particular example. This one doesn't have any hand. Well, it doesn't have any fingers. So it can only move around. It can't actually interact with the stuff in the world. And there's something of maybe about that actual interaction in the world and how important that could be about the things that you can learn. It really gives you a lot more options that you could explore in your world. So that maybe our goal is, well, maybe we want to get more to this Einstein robot here that could do a whole bunch of things, that has hands and explore its environment pretty well. Does that make sense? If some of you think about like the embodiment for the types of things that you want to be able to learn. You know, don't think about it nearly as much as I do. Yeah. Yeah.
How do we go about defining like a minimum standing set of either sensors or actuators that would allow us to reach something that, you know, enables us to go further, right? Like there are certain animals that see like infrared or violet, like that. We don't base sensors to build on top of
Yeah, is this sort of, part of the question is, if we at least know a set of tasks, could we figure out how to reverse engineer what would be needed to solve all those tasks?
Yeah.
And maybe that'll give us some of this base set, but they also, we're human beings. We also tend to get very self-interested in our own tasks. And I mention that because sometimes this tends to get tied to survival. And, you know, there are other things in this world, and I don't know, like weird bacteria that I think exist in like super hot temperatures. Maybe they have better survivability properties than we do. But then we at least start to get into a discussion about what do we mean by surviving in some ways. And there's a lot of discussion in the community about like what these tasks could be and how to describe this. So a lot of this slide here, as I started talking about like design for different robots, but it's a lot about what are you gonna want this thing to do? And then like once you have those tasks, maybe you can reverse think about what does the design need to be. And maybe we'll have a whole nother discussion about humanoid robots or not in later class. Yes.
Strategy. Put it in a people, give it an objective and finds out which way. Put it in a car, then like, give it its objective and finds out the way to the environment. And that's point of the iteration, you know, like learn the environment, not that like learning strategy.
Yes, I mean, that's definitely the point of like reinforcement learning, or, like learning from interaction. There's, and it might be good for the community to learn to reappreciate this aspect more. Like it's not a zero shot thing. It's like, this is an algorithm that given any environment, any reward, and for a dynamics model, if you stick this agent in that, it will figure out the best things to do. Just give it some time. And that's actually a pretty strong claim, to be honest, to be able to do that. And a lot of the, maybe you can generalize, maybe you can zero shot to this and that is usually a kind of, well, it depends on the distribution. It depends on what was in the data set. But no, this system is, it'll collect all the data it needs. It'll figure what are the best actions to take, and it'll give you the optimal policy. Really strong argument. Okay. Any other questions? Okay. For now? All right, so that kind of gets us to a nice segue, but it connects to what we were just talking about. So it's a little bit about like what behavior are the users, which could be us, but anyway, do we want the agents to actually optimize? And this is, we all probably have slightly different tasks we might want robots to be able to do sometime in the future. And we really need to think about, because this specification problem is really hard. It's highly related to a lot of like the preference learning stuff that comes out a lot on the news lately and being able to understand stuff and doing alignment. But we can even talk just talk a bit more practically for a second. Also because this example really gets to this practicality real quick. So we could do like train an agent such that if we give it an image, it'll basically like reconfigure the stuff inside that room such that now it looks like this goal image. So here I'll go for these two examples. So here we've got, don't worry, this is not a picture of my actual room, but you could have it dirty beforehand and you have this one example of when it was clean in the past, and you can always just keep re-giving your agent this goal, and that's the task that we want as a user for it to solve. Okay, do you see any potential issues with being able to use this goal image?
If you add a new object that is not in the goal, you probably don't know. Right?
True. That's definitely one. Maybe there's, I mean, it's hard to tell in this mess over here if you did add a new object or not. So yeah, the agent might not even be able to recognize new objects. We'll hope it might be able to handle some. That's one. Yes. Yes, you must have siblings like I do. Something like that just kind of buries stuff. I'm of course not blaming us as a way to start with. So that's one. So there's things it might not know, ways it can, what people would probably call hacking this reward function to solve it, but not in the way we intended. Yeah. That's very possible. I mean, well, we hope not, but that's definitely a real one. Okay, so these all get to the example here and the one that I like. What happens here? This is a window out into the world. What are we telling the agent to do about everything outside of this room? Are we basically telling it to reverse time? Like go back, reconfigure everything outside of this window back to the time it was from before? We are, like that's the design for this particular task. Make it look like that, every single pixel in the image. If you can't reverse time, go and find a bunch of things that look the exact same. So this is a little bit of what I'm trying to prescribe here. Where like images can be great, and when we're doing things in practice, images very often overspecify what the user is actually trying to tell the agent to do. And it's one of the weaker points of trying to be able to use them. Um, there's been certainly many papers on this, and it's why text might be a better option. But in text, we have the opposite problem where it's often that the goal is underspecified because you could still say clean my room, and the agent then will just dump everything outside of the room, and now the hallway's a disaster. So you often will still need to specify this problem. But we will get more into the details of talking about, okay, what types of goal representations are better or worse? When should you use one or the other? In this case, this one's kind of tricky. One way to solve this that I've done in a paper or two before, which is basically you need to collect more images. We need some distribution over goals such that, okay, if there's a bunch of variation over the images here in the back, a bunch of stuff out there, it's okay, that's not actually important for this goal. If we think about like the log probability of this distribution over states, now the outside, there's a whole bunch of variance in that window. And that's not actually what it cares about. But now we have to design a whole distribution, more work. And I'm lazy as a roboticist. We want to do this as easy as possible as well. Okay, so this is where we do still want these agents to generalize to some of these novel goals. We also, as users and working with them, want them to understand which goals that is meant when the user specifies them. Okay. All right. So now this gets to the point where, okay, we really want learning systems. It would be good to have learning systems that are also basically learning things that are new. A lot of what's been done with reinforcement learning a lot lately is usually doing stuff that we know is possible. Okay, like we use them to play video games. I mean, I was playing video games when I was like 5 or 6 years old, and I was better than most of the Atari, like DeepRL algorithms very early on, very quickly. So are we really making, and we here, I mean like the researchers that are working on this, making lots of improvement? What is the added value of these algorithms so far? And this is, I'm not totally harping on that group because I'm definitely inside of that group as well. But there's lots of papers where we do like imitation learning, which means we already have an example of what the agent can do, and we already know an expert solution. We just want the agent to figure it out for itself. It's good, it shows it can do this thing, but in order to show and maybe generate something new that hasn't been done before, how can we, as researchers, start to think about setting that bar higher and higher such that, okay, now you have to do something, like we want the agent to be able to learn something totally new, something that's for us, but we haven't been able to think of it already. So this is where it's still good to rely on this RL paradigm, because if an environment is created and a reward function is created and we put the agent in there, it should learn to maximize that reward and generate something that's good at that particular thing. But as a group, we can start to think about now giving these agents more complicated things to figure out. So what if instead you could maybe ask your LLM, design me a better battery, and maybe that'll work. Kind of doubtful because it needs a whole lot of data. So then option B is, all right, we need to figure out how to make some sort of chemistry simulator, construct a reward function that describes whether or not a battery is better or worse, and then just set the algorithm basically into this environment, give it a whole bunch of compute and see what it produces. And then maybe manufacture some of those examples, see how well they actually work compared to that simulator. But it means that we want to, when it comes to RL and what RL is more so supposed to promise us is this type of thing. But it means we have to make pretty good simulators or get robots to work in the real world. This fantastic simulator we live in, that is definitely like the evaluation set that we want things to function in. And that's why maybe kind of an open question. Okay, would it be faster to spend our time making simulators in order to be able to do this battery search process? Or would it be faster and better to spend our time working on real algorithms in the real world? Which one of these is going to get us to a better version or design for a battery first? They both require a lot of time and effort. Okay, does that make sense? Comparison? All right. All right, and this is where, all right, and the environment can be seemingly complicated, and it's good to think about it more. So there are lots of examples of RL these days. It's used to, like make cheetah-looking robots be able to run to the right with some amount of speed. That's great. How can the environment complexity start to be increased? If we've got this amazing universe here that we do eventually want to get real robots working in order to get to this spot, yeah, we can either do one of these two things again. We either add more and more complexity to the simulator over time and see how algorithms deal with more complexity in the simulator, or jump to write stuff in the real world and then deal with the challenges of setting up those algorithms to work. And it's maybe like we were saying, it's tied to embodiment, something about the natural way our environment is constructed enables such that these AGI systems end up learning in our real world. Something about other agents, which is obviously pretty important, the way that different agents interact with each other, learn from each other, end up being like adversarial, competitive with each other, ends up kind of maybe boosting some of the things that it would be forced to learn. There's a lot of natural challenges. This used to be a video, but I removed some of those so I don't end up corrupting my slides today. But you can have lava, things like that. The environment is literally changing all the time. This is a great week, an example of that too, because now it's white freezing outside. At least there's sunlight today, so that's a good start. But this having in our actual world, dealing with this abundance of novelty and diversity and changes in other agents is something about what might be important to actually develop like the AI, well, I guess the eye that we have, not the artificial part. Okay, does that make sense? So there's lots of different types of changes. We'll get to some more of these in detail as well. And this is where, okay, this is the good part so far. All right, we've got an example of the environment that we want. It's right out there. Cool, we can probably stick with that one. Now the next question is, what is the reward function going to be that this agent should optimize such that it results in something, at least seemingly intelligent as human beings, or at least what people would define as AGI these days, even though that goalpost tends to change every 3 months. But it's tricky. So one of these, and there is a couple of them that are popular these days, the one that comes from biological motivation is basically coming from people. It seems that what people try to do is be able to minimize their surprise. So in the face of all of this chaos of other agents in the changing environment, the agent tries to keep its local state distribution somewhat under its own control. That way it can, ensure it can feed itself. It has to end up building structures in order to be able to have shelter, deal with things like weather, and all sorts of these things. And it's actually this basically maintenance that the agent must really learn how to accomplish this, or it's going to have to deal with all the weather and the uncertainty over food, things like that quite a bit. There's definitely some other reward functions that are possible, and we'll chat a bit more about those, but this is possibly a start. At least there's a whole body of research on coming from like neuroscientists, things like that, which said like maybe this is the way to do it. The hard part is basically all these awesome reward functions, really, really hard to compute. Most of them are basically intractable, even though they sound kind of hypothetically like a fantastic thing to do. So, and here we'll talk a bit more about dealing with those challenges. All right. Any questions about reward functions? Everyone knows exactly what type of reward function you would give your agent? If you would have one right now? No? Yeah, me neither. Thank goodness I'm not a parent yet. That would be terrifying. Anyway, so, but the last part I'm gonna kind of connect this to is to think about how these all kind of feed into each other. And it's sort of, there is the like typical deep reinforcement learning loop is and great, it learns stuff. If we kind of zoom into the picture inside of this deep reinforcement learning loop, there's a few more ingredients that kind of make this important, especially when we're talking about like deep learning. So it's true, maybe I'll start here, that a generalizable model would be good because then it knows that we can zero shot generalize it to things. We can gather, or the agent can learn from information really well and learn to reuse its information. But how is it going to get this data? How do we know? How does the agent actually accumulate all of this type of stuff? Well, it's going to need some sort of well-structured autonomous learning pipeline that's going to make it and give the agent this ability to kind of explore whatever it wants. So it can experience all the variety and diversity that it can, and then be able to use that data in order to be able to learn basically some good generalizable model. All right. But it may be that that's not quite sufficient enough. This agent will still need, well, that was interesting. This agent may still need, it's blue anyway, but it might need some good intrinsic reward. What's going to motivate it to go and experience all the fun weather outside? Like, are we going to stay inside this weekend? Or are we going to go out ice skating or cross-country skiing or whatever and learn how to conquer more of the nature so that we can bolster the terms of skills and things that we can use to figure out how to get around outside? And it's these kind of connections that go between each other. So this also helps because if you want to do better exploration, often an agent will need better representation so it can explore in a kind of structured way in the world. And the other way around, if it wants to be able to kind of explore some information, having a nice autonomous system helps it cover the space and do more finding, I guess, uncovering more unknown unknowns. And this also goes this way too for some better exploration because you have these models. So these components may all help support each other. And if you lose one of these, it's really hard to still end up with a good version in the other couple components here. Does that make sense? It's good? Okay. So you're all my review committee. I'll submit this to like NSF next week and they'll all be happy with this plan. Sounds great. Okay. So these are kind of some of the general fundamentals. All right. How are we doing? Okay, we still have a bit more time before break. So if you remember, we kind of covered all this stuff last time, so I could make sure to cover over some of the course materials. And then the rest of the stuff is just all references. Don't worry, you don't have to read all these ones. These are just for your own if you want to, okay, you know, Glenn said something about this paper that does good scaling for deep learning. You can actually go check out that paper from the slides. All right, and okay, so then on to our first real topic. Just basically supervised learning. All right,